Welcome, everyone. I'm Rich Berliner. I'm the CEO of Digital Locations, and I'm here today with Sean Bryan from Arizona State University. And Sean, thank you for being with me. What I'd like to do is start off by you talking a little bit about your background and your street cred, if you will, in the satellite business, which from my reading is enormous. And so, let's talk a little bit. What is your title at ASU?
Sure. Yeah, I think it's really great to have an opportunity to be here and have this conversation in this space. Yeah, my title at ASU, I'm an associate research professor here at ASU in the School of Earth and Space Exploration. So I lead our group's called the Sense Laboratory. So kind of broad-ranging interest in remote sensing, wireless communications, astronomy, both software and hardware. So that's kind of the I've got a lot of awesome colleagues here, and yourself obviously, and so it's just really, as you well know, it's really fun to be in this space because there's a lot of different directions it can go.
It's true. All topics that are near and dear to my heart too. So we have a passion for this satellite business. And so, as I mentioned before in our preliminary, our interest is we're doing research on direct satellite to mobile communications. And you seem to be a person in the sweet spot of understanding how hard, first of all, how hard the problem is, because you've got a wireless background in addition to your satellite background. But you're a guy who is working on exactly the kinds of things that we're seeing as the hard problems: antennas, interference from space dust, and a whole series of challenges that go along with this. Which is why we're not seeing companies just shoot satellites up into the air and everything works perfectly from day one. This is still a hard problem, even with a satellite agglomeration or satellite. What's the word I'm looking for? Satellite, a group of satellites.
Right. I mean, the people have all these goals to make these constellations.
That's,
yeah, but as you point out, this is still a tough game. Like aerospace is always going to have challenges. So you can put a constellation on paper, but
right.
It's another thing to put it on orbit, deliver the capability.
So how does your research fit?
Yeah, so I mean, gotten lucky enough to do a lot of different things. So my education background is in physics, so those are my degrees. In grad school, um, I was lucky enough to get to work on a big team. We made a really, really sensitive millimeter wave receiver that we flew on a high altitude balloon. And that was it's for radio astronomy, is to measure the cosmic microwave background. We were measuring that signal at 90 gigahertz and 150 gigahertz. So and it's funny, it wasn't that long ago, but back then we thought, well, that's way above any communications, signals, probably even radars. So, blue sky, we can just, nothing to worry about. And it's even fascinating since then to see, okay, 5G in our pockets is at 60 gigahertz already. It's only going upwards. So that it's a moving target on that side of things, in terms of that particular challenge from interference. But the science payoff is enormous. I mean, we're studying the Big Bang directly, seeing these signals.
Yeah, I was really fascinated when we talked about that offline. But so, and I think what I'd like to do is, if you wouldn't mind, to make sure that we get another interview scheduled when we have more time, but to talk about the Big Bang Theory and what you're studying. But I'm so fascinated by the initial stuff that you said. First of all, working at 90 and 150 gigahertz. So, the question that my team came back to me with after looking at your background and a couple of other folks is there a frequency that is generated by the background noise that's out there? In other words, should we be avoiding, 55, or 70 or 60 gigahertz to try and avoid that background noise? Or is it basically sort of wide open and we're not going to see that kind of interference, which is kind of, an important part to our people, our researchers? What's your thought on that?
Right. It's a good point of interference mitigation. You have to know what the spectrum of everyone is, of of both users, or both, signals of interest, or however you want to view it. Yeah. So for this one, so there are other astronomy signals. So down in radio, like not so much millimeter wave, there's the famous 21 centimeter line that's a single frequency. So for that example, you want to avoid that 21 centimeter wavelength. I forgot what the frequency is, and you're done. From the Big Bang, since it was a thermal process, kind of like a nuclear explosion, those thermal, very hot. Technically it emits at every frequency.
Yeah.
So it's a broadband emission. So we have these broadband detectors, broadband radiometer detectors, is the state of the art there. It would be new. I mean, this hasn't been done yet, but I mean, one way to do it would be if there are narrowband slices that need to be used by a communication user. I mean, perhaps we make a notch filter, on our end, to mitigate that. So it's like that. To me, the narrowband emission might be on the communication side actually, and then we'd want to make sure that our receivers, can that we can coordinate on that, frequency plan, notch them out
Right.
on our side. And the other thing that maybe doesn't get talked about enough is the notion of time. That like if we knew times when there were communication users, well, we can just ignore that time in our data, and then vice versa. If there's quiet time, when we can really jam on the cosmic signal.
Well,
so I think there's at least two, before getting to advanced waveforms, there's at least two things to share on, which is time and frequency.
Right. Well, remember, the early stages of CDMA technology in this country was time division multiple access, which predated CDMA. So you're right in that time is a factor there. So your point is well taken. Everything emits at every frequency. So that's something you have to take into account. One of the questions I had that I think is very relevant for you, especially, is, the experiments that have been done on terrestrial wireless with millimeter wave have been basically a failure, in my judgment. In other words, if you heard, I won't mention the name of the company, but who was advertising 5G systems before they actually had put any in, and we're talking about how great it was. But when they actually put it up at 28 gigs, it broadcast for a block and a half. So it really wasn't a viable situation. And I know that the power output is a big factor in that. But if we're talking about satellite transmission going in a LEO, a low Earth orbit, to a mobile phone, how do you look at the ability for that signal to be able to come down? What is a low Earth orbit satellite at 200 kilometers, 300 kilometers, something like that? How do you look at the ability to have enough power to get to my mobile phone and then back up again?
Right. Yeah, it's true. Because you mentioned the 24 gigahertz that gets used. And then, it has the exact limitations you talk about. So from a mobile user, terrestrial, it's like you said, I mean, it's got to be line of sight, and then terrestrial, that can be, hundreds of yards, if you're lucky, if there isn't a tree,
Exactly.
There's this other obvious one that hits me personally is you have to take the device out of your pocket, right? Because even the cloth is kind of your, so now on the contrary, a concept of operations that would maybe make more sense would be if you say, well, the user has to take the phone out of their pocket, and then there really is a line of sight to the satellite, there probably isn't a tree, or less likely. And then at 90 gigahertz or 150 gigahertz, I mean, the reason we use those is that the atmosphere really does, transmit those frequencies pretty well. So that's both an opportunity. Like someday someone's going to make a 90 gigahertz link. It's a higher frequency, so you can, use a parabolic antenna, maybe up there at least, to form a beam, which could reduce the transmit power a lot. So there's a big opportunity there. And then for radio astronomy, dang it, like now we don't have that window to ourselves anymore. So especially 90 gigahertz really seems like someone's going to get that right at some point. Both for satellite and a ground equipment.
In our research, we're looking at the antenna situations, both on the satellite and on the ground. And one of the important things, and again, I'm not an expert, I'm not a technical guy at all, but it's the link budget aspect, the power usage, and those types of things. And it seems like you've been poking around and testing that sort of thing with your research. And how does that play out to you in terms of, we know it's a hard problem. We know you've got to tinker to get it right. But from your standpoint, this is tough, but it's definitely doable given the fact that you have a number of different issues that you can moderate and increase and decrease to make this all work. How do you view that? Am I off base, or am I on target with that?
No, I think you're we're thinking about it the same way. Hopefully we're both right. So if we had Excel open, the two of us, we could work a link budget and change that. The things that I think that have changed recently, say at 90 gigahertz or at millimeter waves in general, is a lot of groups, both at national laboratories and private companies, university groups, like the transmit power you can get from like a plausible off the shelf system at 90 gigahertz, like that keeps going up. I mean, it's amazing that it's like multi-watt. I mean, it's just that's a big deal, like versus millimeter waves even 10 years ago, we would always say milliwatts, right? So that's a huge change on that end of the link budget. And then I think a couple things in parallel. People are more comfortable with the idea of deployable antennas in space, even with the exquisite, at such a high frequency, you need really exquisite control to make sure that parabolic reflector is just the right shape. People more comfortable with that. And then colleagues here at ASU and then around the world, like metamaterials continue to improve in this area. And eventually someone's going to put that on orbit, like that technology will get used. So that in terms of increasing the antenna area and transmit power, that's changing quickly and in a good way and out there in the open, not just, I'm sure defense, organizations have capability beyond this, but out in the open, it's really amazing what's out there.
Yeah, it's funny. I had one of these podcasts this morning with a researcher from Stanford who used the term that I hadn't heard before, which is origami in space. So that
right.
you got this nice little fortune cookie all wrapped up, and then when it gets up there, everything pops up and you've got this giant array. And what we're looking to do is to not necessarily have to have companies put a football field in space, but to be able to use metamaterials and the right link budgets, power, and all that goes along with this to balance those to make it work properly so that it does go to your phone, maybe even certainly has to get through your clothes to us, but also, using massive MIMO and beamforming and a whole series of techniques. So you've got basically a very technical issue of all the different things you've got to consider. If I rejigger this, how does it work with this? And if I move that, how does it do to my link budget? So that's where, our researchers' heads are at. But, for someone like you that's, looking at the Big Bang Theory, this seems like, kindergarten cop, if you will.
Maybe. I mean, it's amazing how it's a similar story on the radio astronomy receiver side. Just that we're always wanting more sensitivity, so it's not a transmitter or a receiver, but like we're always wanting, better low noise amplifiers, better LNAs, or the system in grad school, we use direct detectors. Like we didn't even have an LNA. We would just have these cryogenically cooled detectors that would, the 90 gigahertz, we cooled them so much that the 90 gigahertz is enough to actually heat them up a little bit. And that's just a very direct detection. So technology really is core to this, to the story for, radio astronomy receivers as well. I think that's what's let me realizing that more and more as I go on in my career, like that's what's kind of giving me the good fortune to be able to work in both spaces, is that they're more similar than I might have guessed starting from one.
What is the physical research you're doing right now? What are you working on? If I might
I had a couple projects going. So one is a millimeter wave receiver. We haven't mentioned yet another thing these millimeter wave radiometers are good for is imaging the atmosphere, as a weather imaging system. So I have one of those going where we, again, took some ideas from radio astronomy and tried to bring it into that space. We're flying that on high altitude balloons as well. Pretty exciting. That's going. And then on a totally different thread, still space though, I'm writing some software for a NASA mission called SphereX. That's an infrared astronomy satellite. But it's another good, as you alluded to earlier, it's like challenges at the system level or the mission level are often, really important to get right. So this infrared astronomy mission is such a big mission. It's been really cool to see, to play my little part in that, but to see some just really outstanding engineers and scientists, perform the system. So that's what I got. That's the day job at the moment. Yeah. and it's both really fun.
It seems like a handful. I mean, you think about, what we're talking about here is maybe it's 60 gigahertz, maybe it's 90 gigahertz that's right for these uses. And then you've got the effect of weather. So you need to potentially either increase power, to hop frequencies, to do a whole series of things. But your research really struck me as fundamental to how we're going to solve this hard problem of satellite to mobile. I would really like to reserve an opportunity to do another one of these with you and talk nothing but the Big Bang Theory and your background in that whole thing and what you're doing with radio astronomy in that setting. So I hope you will come back and do this again soon. But I've taken up enough of your time, and I really appreciate it. You seem like a really, really bright guy, and have a lot of good things ahead of you in this. So again, I'm here with the opportunity to talk to one of the premier people in the satellite. What is the radio telephony, or what do we call the radio astronomy? Radio astronomers in the business. Sean Bryan from ASU. Sean, thank you so much for being on our program today. I really appreciate it.
Thank you so much for the opportunity and the kind words. Yeah, well, we'll talk again soon.